Hey everyone, and welcome to this crash course on ROS2 control. If you want to work with ROS2 and real hardware, you will need to use ROS2 control at some point. And maybe you have already started to learn it, but you feel completely lost. Well, I would say this is quite normal and you have come to the right place. Note that this is not a tutorial for complete beginners. You need to actually have some ROS2 basics already so you can clearly understand this. Now, what will we do? In this crash course, we will start with a quick ROS2 control overview, and then we will dive directly into the code to set up a ROS2 control stack for a mobile robot. I will give you the URDF for the robot as a starting point. To set up this ROS2 control stack, we will use a mock component, which makes it easier to begin. This crash course is great to get started and understand ROS2 control, and if you want to go further and create your own custom hardware driver, hardware interface, and controller, then I have a much bigger course for you, which contains 7 hours of video content, lots of practice and projects, and downloadable code templates that you can use for your own projects. You can find the course link in the description below. Alright, and now let's get started with the crash course. First step, let's understand how ROS2 control works with a global overview. So let's start with this. On the left here, you see we have our application. So what's the application? It's, for example, an application like navigation stack that's going to give you a command velocity for a robot to move in a room. Or you can have an application that's going to control a robotic arm. Well, that's kind of the higher level application in ROS that's going to tell your robot what to do, but not how to do it. Okay? So we have this, we have the application. On the right side here, I have my hardware, so it's a brown box, it's just the hardware, the piece of hardware. So it can be a motor, it can be a sensor, or a combination of motors and sensors. Well, that's the hardware for our robotics system. Now, well, there's a lot of things missing in the middle. So how do we pass the command from the application to the hardware? And let's actually start not from the application, but start from the right side, from the hardware. And first, we will need to add a hardware driver. So here, this has nothing to do with ROS really, it's just a piece of code like a Python, C++ code that's gonna allow your computer to talk to the hardware. So for example, you need to start communication with the hardware using a certain protocol like serial, I2C, CAN bus, etc. You're gonna also have some functions so that you can correctly kind of translate a command into something that the hardware can understand. Okay, so hardware driver is something that's not really specific to ROS, it's something you will do for any piece of hardware. And then here we have ROS2 control, okay, between the application and the hardware driver. What do we have inside ROS2 control? We have two things. So still going from the right side, we have the hardware interface. So the hardware interface is the, well, as the name suggests, is the interface to the hardware. So it's going to be directly communicating with the hardware driver. Sometimes those two are kind of mixed together and are the same thing, but we're going to also see later how it's best to have a pure, let's say pure C++ hardware driver and then a hardware interface that's going to work with it. So hardware interface is basically also just communicating with the hardware. It's a piece of code inside your ROS2 control architecture that's going to allow you to send commands to the hardware and to also read the data from sensors or for encoders or stuff like that. And then to complete this, we have the controller inside ROS2 control. And so the controller is going to take a command from the application and it's going to do, for example, interpolation. It's going to make sure that the command is running smooth, maybe with smooth accelerations, velocity, all that stuff. So this all the stuff you can decide. You can create your own controller and you can also use existing controllers. So there are a lot of existing controllers we're going to see, for example, to control a differential drive robot, a robotic arm, etc. So now the global overview is kind of finished. Okay, inside ROS2 control, you have the controller, which is taking the command from the application and saying how the command should be outputted to the hardware. But the controller doesn't talk directly to the hardware. So it's going to send that to the hardware interface. And then the hardware interface is going to talk to the hardware and also send the feedback to the controller. Now, what you might see if you go to ROS2 control documentation and stuff like that, you might see something like this. We don't necessarily have one controller and one hardware interface. We can have many controllers and many hardware interfaces. So if you have a complex robotic system with for example, a mobile base, a robotic arm, some sensors, maybe even a simulation here and there. Well, you can do all of that with ROS2 control. You can have many controllers that communicate with different hardware interfaces, which are also communicating with different hardware drivers. Okay, so ROS2 control is very modular, very scalable. You can do lots of things with it. But to get started, let's actually come back to this, which is already complex enough, and let's try to understand this first. Now, to understand this ROS2 control box, I'm just gonna zoom in. We have, as I told you, we have a controller and we have a hardware interface. How this is going to be connected together is we're gonna have also in ROS2 control what we call the controller manager. Okay, so you're gonna have your controller, which is either something that you write yourself or you get an existing controller. Then you have your hardware interface, and you're gonna start everything with the controller manager. It's gonna take those two, and then you can say you want to bind the controller with this hardware interface, and the controller manager is gonna do all of that for you. Okay, so in the end, what we need to do with ROS2 control is we need to provide a controller, we need to provide a hardware interface, and then with the controller manager, we can start everything. So coming back here, that's everything we need to do to adapt the robot to ROS2 control. I'm gonna give you an example with some units, okay, because it might still be a bit confusing. So let's say that the application is navigation for a mobile base, and the application is sending a command velocity topic. So we have a command velocity topic with a, let's say, a twist message. You might already know this message. And it's gonna send a linear or angular velocity in meter per second and radian per second for the robot. So for example, going forward with a speed and then turning left or right with a certain speed. Okay, this is specific to the robot. Then the controller is going to transform that velocity, but for a velocity for each wheel. So the controller is aware of the dimensions of the robot, how many wheels we have. So do we have 1 wheel, 2 wheels, 14 wheels? It's gonna take the command from the application and say each wheel at specific time must run at X radian per second. Okay, so here we are already in the how, and we are already specific to the robot. But still, at the controller level, we don't know what hardware we're talking about. We just know it's specific to the wheels for that robot, but we don't know the hardware. Then we're gonna send that command to the hardware interface. And this is gonna be the connection between the controller and the driver. And the driver is gonna transform that command for each wheel into something that the motor can understand. So for example, an RPM, so rotation per minute, and then it's gonna use a certain communication protocol to send that to the motor. And when we go back, it's also gonna read an RPM that's gonna be transformed into, for example, radian per second. That's gonna be sent to the hardware interface, and then the hardware interface is gonna send back to the controller, and the controller can do kind of a closed loop control to send the next command. Okay, so with this, you can kind of see that each layer is only handling one thing, and the more we go right, the more we are specific towards the hardware, and the more we go left, the more we are just global about the application. Now you can see we need to specify controller, hardware interface, and a hardware driver. That's a lot of things. And to start with ROS2 control, what we can do is we can just use a mock component. So a mock component is a fake and perfect hardware, and it's useful to get started. Basically, we can skip the whole hardware interface, hardware driver, we don't even need the hardware. We just need to set up a mock component that's already existing within ROS2 control. And thus, we can test our ROS2 control architecture with a controller, the mock component, and we can start everything. And note that when I say it's a fake and perfect hardware, you could think that it's kind of a simulation. So yes, somehow it's a simulation, but it's a perfect simulation. It's not a real simulation like Gazebo where you have physical constraints, gravity, etc. Okay, this is just a short circuit before the hardware, so we can develop our ROS2 control stack one step at a time. I will do a quick recap of what we need to be able to run and work with ROS2, and we are going to install the packages for ROS2 control. So I will go quite quickly because you should already know how to work with ROS2. Those are the prerequisites for this course. So first of all, we need Ubuntu. Here I have Ubuntu 24.04, and I recommend that you have at least this version or a more recent one. I have installed it, so this is the native installation with a dual boot. Okay, it's probably much better to have that than to have a virtual machine. Then you will need to install ROS2, so the corresponding ROS2 version. For Ubuntu 24, that's ROS2 Jazzy, but if you have another Ubuntu version, then install the corresponding ROS2 distribution. And so for ROS2 Jazzy, I have documentation here. You just follow the Ubuntu dev packages page on the documentation, okay? You're gonna, well, you might need to set up the locale, enable some repositories, set up the sources here, install the development tools, then update upgrades, and you just install here. I have installed ROS desktop. All right, so that's what we need. And then for the environment, you see we need to source this setup.bash script, and I have already put that into my bash RC. At the end, you see what you can ignore this commented line, but I have already the line to source the setup.bash script so that we can use ROS2 in all the terminals. Great, so that's it for the ROS2 installation. And now we are going to install the packages for ROS2 control. So sudo apt install ROS, and then the distribution. So for me, it's Jazzy. And then you have ROS2 control. We are going to install this one, and then ROS distribution, ROS2 controllers. So, okay, so we are going to install ROS2 control and ROS2 controllers. Press enter. And well, I've already done that, but for you, it's going to install a few new packages. And that's it about the ROS2 packages we need. As you may already know, the URDF is one of the first things you need to have for a robot to work with ROS. In the URDF, you describe the different properties of the robot, mainly the links, which are all the independent rigid parts, and the joints, which represent the connection between those links. Now, to set up ROS2 control for a robot, well, you will need a URDF first. As URDF is a prerequisite for this course, and as I want to keep this course focused on ROS2 control, I'm giving you directly a package with a URDF for a mobile base. So you can download here section 2 starting code, and we're gonna extract, and you can see inside we have my robot description package. Okay, so what I'm gonna do is, well, I'm gonna go back to my home directory. Let's do that from the terminal. And we are going to create a workspace. So for example, ROS2 workspace. Okay, and in this, so let's go to the ROS2 workspace and we create a source folder. Okay, we have a workspace. So this you already know. Now what I'm gonna do is take this my robot description package. I'm gonna copy and paste it inside the source folder here. Okay, if I do ls, if I go to the source, I have my robot description package. Okay, so you create a workspace and you put the package here in the source folder of the workspace. We're gonna go back, and before we check the code, let's just see what we have. Let's just build it, Qualcomm build. Then we're gonna source the install setup bash, which we can also put inside. So let's open the bash RC. At the end, okay, I already had this commented. So you have the line to source the global ROS2 installation, and then the line to source your workspace. As usual, we save the bash RC. Okay, you make sure that you have sourced, or you open a new terminal, or use source the script, or you source the bash RC. And then we can do, I'm just going to do cd, we can do ROS2 launch my robot description. You should use the auto completion here. You see, if it works, then it means that the build was successful. And then we have display.launch. And then XML. There's a Python version as well. We're going to start the XML. It doesn't matter. You start this. Okay, and this is going to start RVs. And you see our robot. So it starts RVs and also a joint state publisher window. Okay, we can put that side by side. And what you see here is we have a mobile base. That's what we're going to use as a starting point. So we have a base link here, 2 wheels, and a caster wheel. Okay, very classic stuff. And then you see we have 2 joints. So revolute joint, actually continuous joint here for the right wheel and the left wheel. All right, so this is quite classic. It should not be really new to you, okay? So what we have is basically a URDF that's configured also with the TF, and that's gonna be the starting point for any of your ROS2 application. Now let's have a look at the code. I'm gonna stop that here. Let's go to the workspace and I'm gonna open, so as usual, I go to the source folder of the workspace and I do code dot. Okay, that's the best way to start the workspace here. And in my robot description, what do I have? Well, we have the package.xml, the cmeclist.txt, and you see here, we have 3 more folders, launch, RVs, and URDF that I install here with inside the cmeclist.txt with the install function. Okay. In the URDF, we have, so the main file is myrobot.urdf.zacro, which includes common properties and mobile base. Okay, we're gonna use Zacro here. In common properties, I have what? Material blue and gray, so we have some material tags. So not much, is just for the colors that you see on RVs. And then on mobile base, we have what? Well, first we have properties with the dimensions, okay, for the base, the wheel, etc. And then we have all the links and all the joints. Okay, that's it. You see we have the base footprint and then the base link. We have a macro for the wheel, so then we have the right and the left wheel and the caster wheel. Then we have the joint, okay, between the base footprint, the base link, and then between the base link and each of the wheel, so the right, left, and caster wheel. All right, so that's the URDF part. Then we have also an RVs config, so that when we start RVs, we can start with the view already like it was. And then in the display.launch, so either the Python one or the XML one is the same. I'm going to use the XML, it's much easier. You see what do we have for now here. I have variables to find the URDF path and the RVs config path. But basically we start what? We start the robot state publisher. Okay, that's basically the first node you're going to start in a ROS application. Robot state publisher, and you provide the URDF. Then we have a joint state publisher GUI, so graphical. This is just to visualize the movement of the joint states. Okay, we're going to have to do that also later by ourselves. And we start RVs. Okay, so this launch file is not the launch file we're going to use for our application. It's just the launch file to display the URDF. Okay, and so that's basically the starting point. In this lesson, we are going to do the first step to adapt the robot to ROS2 control. We are going to add a ROS2 control tag in the URDF. So let's go back to our workspace. Let's open it here with VS Code. And well, you have the URDF here with, as you see, a main Zacro file that includes the command properties here and all the links and the joints for the mobile base. So I have named my robot mobile base. Okay, so this part of the robot is named mobile base. Here we are going to add a ROS2 control tag. But actually I'm not gonna add it directly inside this Zacro file. I'm gonna create a new one. So let's create a new one. Let's name it mobile base dot ROS2 underscore control dot Zacro. Okay, this is something that's quite common to do. And then that's a Zacro file. So I'm gonna start with, I'm just gonna take from any other file. I'm gonna start with the XML tag and the robot tag with the Zacro here URL. I'm just gonna take that and close the robot tag. Okay, let's save. We have a Zacro file. And before I write anything here, we're gonna use it in our main Zacro file. So I simply need to do a Zacro include and then file name. That's gonna be mobile base dot ROS2 control dot Zacro. Make sure you don't make any typo here. And let's save this file. Okay, so in the main file, we include all those 3 files. Great. So that's a great way to separate our code and make it cleaner. Now, let's start this ROS2 control tag. So I'm gonna add a tag that's simply ROS2 underscore control. and I need to give a name. So for the name, I'm gonna use mobile base, okay, and then hardware interface. This name is not really important for now. You can just put the name of the robot or the system inside your robot and then hardware interface, okay, as a convention. And then we need to provide a type. So type can be sensor, actuator, or system. So what does it mean is if you're gonna control just one sensor that you're gonna read data from, you can use sensor. If you control just one actuator, like just one motor with this interface, you can use this. But if you control multiple joints or multiple sensors or multiple, well, more than one thing from the same hardware interface, you're gonna use system. You don't need to worry about that for now, just use system for everything. Because system includes sensor and actuator. So don't worry about this, just use system. You open and you close, ROS2 control. All right. Then we need to add a hardware tag. We open and close the hardware tag. In this hardware tag, we're going to use a plugin. And what's inside this plugin? So I'm going to first close. We need to provide the hardware interface. So if you remember what we saw before is that you have a controller in ROS2 control and you have a hardware interface. Well, after you develop a hardware interface, you're going to be able to put the name of the hardware interface here, but we haven't developed a hardware interface yet. We're going to use a mock component. So we're going to write mock components like this with an S / generic system exactly like this. Okay, so this is lowercase with an underscore, and this is camel case, upper camel case. If we use this plugin, well, it's something you cannot really guess, but you need to also use param name. We can give some parameters to the hardware interface. That's gonna be calculate dynamics, and value is true. Okay, so there's not so much to understand now. You just know that you have to write this, and this is going to be the same for any robot. So once you just know how to write the ROS2 control tag, it's going to be the same. You give a name, a type, we use system by default, and then for the hardware interface, you just use mock components to start. And after this, we need to provide the interface for each joint that we will want to control with ROS2 control. Okay, so those joints are going to be passed to the controller. So I'm going to add a joint here, make sure that the hardware and the joints are separate. Okay, the joint is not inside the hardware. And then name. And that's going to be the exact name of the joint that we have in the URDF. So for this, I'm going to go back here and I'm going to go to the joint, base, right wheel joint. Okay, so I can start with the right or the left wheel, which is the same. Let's go here. Okay, I open and close. And in this, I will need to specify tags such as command interface name. So what is this? Well, in this ROS2 control tag, you're gonna set what kind of hardware interface you use, which for now is a mock component. And then you're gonna specify command and state interfaces for each joint that you will want to control, and that's going to be passed to the controller. Okay, so it's kind of a URDF configuration that's going to be passed to the controller to see, well, what kind of common interfaces. And here you can basically write position, velocity, I think acceleration maybe, and also torque or effort. So how you're going to control the joint, okay? Because this is a wheel, we're going to give a velocity. So I write velocity. So basically what command you want to send to that joint. Position, velocity, something else, here it's velocity. And then we also have state interface. What data we're gonna read from the joint. And here I'm gonna also put velocity. So if you wanted to do an open loop control and the controller is only open loop, you could just send the command and not have any state. Here is going to be a closed loop control. So the controller we're going to use, we're going to see that in the next lesson, is going to need to send a velocity command and receive a velocity state. And actually, I'm going to add another one here, state interface name position. Because for the controller to work, so that's specific to this controller. For the differential drive, it's gonna also need to know the position of the wheel. So we're gonna send velocity and we're gonna read position and velocity. We're gonna do the same thing for so this is the right wheel. We're gonna do the same thing for the left wheel. And because those are gonna be the same, I'm just gonna copy the joint tag and paste it here and replace that with the name of the joint for the left wheel. Like this. And that's gonna be it for the ROS2 control tag. So to recap, you give a name, it's not so important for now. System for the type. You set the hardware interface, which for now is a mock component. And then for each joint, you put the name of the joint and what kind of command you want to give and what kind of state you're gonna receive from that. Now that you have added a ROS2 control tag inside your URDF, we're gonna do the second step here, which is to add a controller config, okay, to specify which controllers you want to use and set different parameters for those controllers. All right, and with this, we would have the complete ROS2 control setup with one side the controller and the other side the hardware interface specified here. And once again, if things don't make sense for now, well, it's definitely okay, it's normal. The thing is, when you learn ROS2 control, there's a lot of stuff that you need to start by just, well, using what's existing, using what works, not necessarily understanding it, but then as you progress and then you come back to the big picture, then you will put all the pieces together, okay? So just follow along, we're gonna make this work and you're gonna understand better as we progress. So how do we specify a controller configuration? Well, for now we only have one package, my robot description. Okay, in this package we have the URDF and also the ROS2 control tag because that should be in the URDF. Now we're gonna add a config file. So what I'm gonna do is I'm gonna create a new package. So I'm gonna come back to a terminal. Let's go to ROS2 workspace and source. And I'm gonna create a package with ROS2 pkg create my robot, so the name of your robot, and then bring up. Okay, so you've already done that to create launch files and also YAML files. That's what we're gonna do right here. So we create our bring up package. Maybe you already have one, then use this one. Okay, so I just do a ROS2 pkg create, and then I'm gonna go inside my robot bring up. And what do I have here? Well, I'm gonna keep the cmake_list.txt and keep the package.xml, but I don't need include and source. So let's remove those. Remove include and source, and I'm gonna add a config folder. Okay, I'm gonna add the launch folder later. Let's do things one step at a time. So let's go back to our VS Code here, my robot bring up. I have my config folder, and then what I'm gonna do in the cmake_list.txt, I'm gonna clean this a bit so I don't need the build testing and those comments. And I'm gonna add the instruction to install. So install, that's gonna be directory config, and then destination. That's gonna be share / and then $, curly brackets, project name, which project name is basically you see the name of the package. I can add a slash here if I want to. All right, so just install the config folder inside the share repository here for this package. I'm gonna save that, and that's it. Okay, so this should not be new for you. You've probably done that already several times. Now in my config folder, I'm gonna create a new file, and well, I'm gonna name it my robot controllers.yaml. Press enter. Okay, so that's gonna be a YAML config file, and you can name it as you want. Here, just something controllers. So here it's for my robot. So the name of the robot is my robot. So I just name it like this. And then the first thing that we're gonna do is we're gonna add parameters for a node called controller manager. Okay, so if you remember in the introduction of this section, I have introduced the controller manager to say that this controller manager is going to kind of start the different controllers and bind them with the hardware interfaces. And we need to specify some parameters. So I put ROS and then double underscore parameters. The first parameter that we're gonna need is update rate. And that's one of the most important. So basically your controllers, what are they gonna do? They're gonna read something from the feedback or read something from the command that's being passed from the application. Then they're gonna update the next command and they're gonna write the command to send to the hardware, okay? So basically it's a loop of read, update, write. And I'm gonna come back to this later. And so how often do we update the controllers? So if I put 10, here that's gonna be an integer, it means 10 Hertz, so 10 times per second. So depends on the application, this might be enough or quite slow. I'm gonna put 50, okay, 50 times per second. In some applications, like if you have a robotic arm and you need a real, almost like real-time constraint, sometimes it goes up to 500 or 1000, even sometimes 1.5 kilohertz I've seen. So, well, that's gonna depend on your application. But to start, something like 50, 100 is gonna be enough. And after this, so well, we have only one parameter for the controller manager, but we're gonna add more parameters which correspond to the different controllers we want to start. Now you might ask, what controllers? Well, where are the controllers? And that's a very good question because the documentation actually doesn't really exist at the time of recording this course. What you have to do is you have to go to GitHub. So you can easily find this. Okay, ROS2, you just type ROS2 controllers on Google, you just find this under the ROS controls GitHub repository. And what you can find here is different folders. And all those folders here, they are all existing controllers that you can use. Okay, and those are gonna be very useful. And so I'm gonna show you which one we're gonna use now and also how to be able to use them by actually reading the necessary code inside those folders. Okay, that's the documentation that you're gonna use. So it's not optimal, but actually it's not that bad once you understand just how to use it. And so you can see we have, we're gonna use the Diff drive controller because we have a Diff drive robot. You have stuff like force torque sensor broadcaster, you see gripper controller, GPIO controller, you have tricycle controller. Okay, you have lots of different things, velocity controllers. So we're gonna use a few in this course, and then of course you can use more. Those controllers that you see here, they are working quite well, and they are actually enough for most use cases in robotics. And the first controller that we're gonna use is the joint state broadcaster. So what is the joint state broadcaster? Well, it's going to publish the joint states for each of your joints here, so the left wheel and the right wheel that we have. And now you might think, well, why do we need that? Well, because actually nothing is going to publish the joint states if you don't do it or don't specify to do it through a controller. Because if you look at what we have in our My Robot description, in the launch, in the display launch XML, what we have started to just display the robot is we have started the robot state publisher. The robot state publisher is going to listen to the joint state so that it can publish on the TF. Okay, so somebody needs to publish the joint states. What we have done here in this example is just to use a fake joint state publisher with a graphical interface, so we can, well, fake the joint states. But we don't want to fake the joint state for a real robot or real project with ROS2 control. So we need something that's gonna get the data from the hardware and publish it on the joint state topic. Okay, and that's where the joint state broadcaster comes in. And note that, well, this is a controller, but a controller doesn't necessarily mean that you're gonna control a hardware in the way of, for example, moving a motor. Okay, controller can just be something that's gonna read some data from the hardware and publish that on a topic. Okay, that's also a controller. And so we're gonna use the joint state broadcaster. Actually, you're gonna use it probably in all your projects because as soon as you have joints in your URDF, basically you're gonna want to publish the joint states for those. So you're gonna have the joint state broadcaster. So what we do here, you can copy paste in basically all your projects. All right, how do we use this? Well, you go to the joint state broadcaster folder here in the package, and you see we have a XML here, we have a plugin, joint state plugin.xml. You're gonna click here and you see some kind of, well, XML file here. We're gonna use something similar when we create a hardware interface, okay, later in this course. But for now, let's just keep things simple. You see we have joint state broadcaster and we have a class with a name and a type. You're gonna use the name, okay, the thing with the slash here. So joint state broadcaster / joint state broadcaster. That's gonna be what we're gonna use in our file. So we go back. I need to name it. I need to give it a name here. I'm just gonna name it joint state broadcaster. Okay, this is the name that we're gonna use when we start it here from the launch file. So you can name it ABC if you want. You just need to use ABC later in your launch file. But we're gonna use something that makes sense. And then, so I'm gonna actually go back to a new line, new indentation. I'm gonna put type. And for the type, I'm gonna use the name of the class here from this XML file. Okay, so I copy this and I put it right here. Okay, so make sure that you put the name, so the name that you create for the controller, also under the parameters of the controller manager here, so it can be started. And then under the name that you choose, you put type, and then you write the type here. Okay. Then for a controller, you can also specify some parameters. So if we go back here, then you go to the source folder. In the source folder, you have the CPP file, but you also have a YAML file. In this YAML file, you have all the different parameters you can use with the type, the default value, description, etc. So I'm not going to go through all of them, just show you the joints. Okay, so the joints is a string array with an empty array by default. Okay, and you can see that if it's left empty, all available state interfaces will be published. Okay, I'm coming back here. What are the state interfaces? It's gonna be, if I go back to the URDF and the ROS2 control tag, state interface, basically we're gonna have the position and the velocity for each joint. Okay, and by not providing this parameter, we're gonna publish all the joints, which is what we're gonna do for now. We might change that later, but for now, we're just gonna not write this parameter. Okay, so I'm not gonna use any parameter for this joint state broadcaster. We're gonna use parameters for the next controller that I'm gonna do now, so you can see how to add them. You have already made a lot of progress. Congratulations. Now we are about halfway through the crash course. I hope that you are learning a lot, and I also hope you like the course. If you find it useful, then you might want to check out my bigger ROS2 control course, which contains more than 7 hours of structured video lessons and which will take you much further into the understanding of ROS2 control. The course will also teach you how to create your own hardware interface so you can bridge ROS2 control with your real hardware. Well, I will leave a link in the description if you are interested. Alright, and let's continue with the video. Now let's add a second controller. Okay, I'm gonna name it. So I just go back to a new line here, still under the parameters for the controller manager, and I'm gonna name it Diff drive controller. Okay, I just name it as I want. I just make sure that I give a name that has a sense. And then type. What's gonna be the type? Well, we're gonna go back here, go back to our ROS2 controllers. And we're gonna use the Diff drive controller. Okay, this one is a quite common one. And you can probably find lots of examples online with different configurations for that. So we go here, you see we have a XML plugin file, which is the same as the other one. And you have Diff drive controller here with a slash. That's the class name that we're gonna take and put right here. Okay, so now when you see a file like this, you understand how it's made. And then I'm gonna go back here and I'm gonna go back to the Diff drive controller, to the source folder. We have more files, but we're gonna only open the YAML file, which contains all the possible parameters. And those are, you can see, we have more parameters. And this time we're gonna specify a few of them, okay, because some are really important. Now, how to specify the parameters? Well, what I'm gonna do simply is I'm gonna go back to a new line here. So after controller manager, and I'm gonna put the name here, Diff drive controller. So the name I've created here, even if it's the same name as you see this kind of namespace, those are not the same thing. Okay, it could be any different name. So I put Diff drive controller, and then two spaces, ROS underscore underscore parameters, and then two spaces, and we're going to add the parameters for this controller here. Okay, so basically when you start this, the joint state broadcaster is going to be a node, the diff drive controller is going to be a node, and you just put the parameters for that node. Now, what parameters are we going to use here? Well, let's go step by step from the beginning. You see we have left wheel names, okay, in plural, and that's the string array. Because for a diff drive robot, well, in this case, we just have one left wheel and one right wheel. But you could have two wheels on each side and still have a differential drive robot, okay? If both wheels are turning at the same time, then the robot can work exactly the same. You can have 2 wheels, 3 wheels, 6, as many as you want. So we need to add the left wheel names and put an array with the joints that correspond to the left side. And you see the default value is empty. So if we don't specify this, it's simply not gonna work. So I'm gonna go here, left wheel names. That's gonna be an array here. And with quotes, I'm gonna add the joint for the left wheel. So I go back to the URDF here, mobile base, and you see base. So make sure not to confuse left and right. Base, left, wheel joint. I take the name and I put it right here. Okay? And we would have the same right wheel names with, this time is gonna be base right wheel joint. Okay, so this is because I have named it like this, but of course in your robot, if you have used a different name, you use the name you used in the URDF. Okay, so the first very important thing is what are the joints that we need to control? Okay, so where are the wheels? Because this controller is going to control the wheels. It needs to know what it needs to control. We go back here. Then we have two more parameters, wheel separation and wheels per side. So, wheels per side, actually, we don't really need it, it's 0, but if you have more than one wheel per side, you probably need to set this one. But we're gonna use wheel separation and wheel radius. Okay, those are really important values. You see, set to 0, so we need to provide that. So I'm gonna put wheel separation and wheel radius. Now, what is the wheel separation? I'm gonna go back here to the mobile base and let's see what we have. So you could start this, you could start the display launch XML to see it again. Okay, basically the wheels are on each side of the base link. And the base link, we have the base width, which is 0.4. Okay, and then the wheels are on the outside. Okay, so the wheel length is 0.05, meaning that actually the joint for the wheel on each side is half of this from the base. So 0.025 on each side, which means that the total distance between the two joints is 0.025 multiplied by 2, which is 0.05 plus 0.4. Okay, if you don't understand this, I encourage you just start the RVs with the display launch XML and visualize it for yourself. And so wheel separation, we have 0.45 centimeters. This is very important. If you are wrong with this value, well, it's still gonna work, but the velocity output is not gonna be correct. And then the wheel radius, this one is easy because we already have wheel radius here, 0.1. Okay, it's the same thing. Then I go back here, and what else do we have? Well, we're not gonna use the wheel separation multiplier and all that stuff. I'm gonna go down here, and I'm gonna specify the ODOM frame ID and the base frame ID. So I'm gonna put ODOM frame ID and base frame ID. Why do I do this? Because, well, the diff drive controller is going to do actually two things. First, it's going to control the wheels, okay? So it's gonna receive a command velocity, and it's gonna output that to basically a command velocity for each of the wheels. So it's gonna send a velocity and receive a velocity back to create a closed loop control, okay? Now, if I go back to the interface, that's why we have a command interface velocity and a state interface this one, state interface velocity. Okay. But it's also going to do a second thing, which is to publish the odometry. What is the odometry? The odometry is simply the distance between the point where you started the robot and where the robot is right now. So it's going to actually publish a new TF, which we call odom. Odom for odometry. And to publish this TF, so I think is that I have not read the code entirely for the controller, but I think that's why it needs to have the position, so the state interface position that we have specified here to actually compute the odometry. Okay, so basically the command interfaces and the state interfaces we have specified are kind of specific also to the controller that you're gonna use. And I know this is a bit of black magic, but well, that's just how it is. How do you know that? Well, it's just with experience that you know that. So now that I told you, well, for the next time, you know it. All right. And so this is going to publish an additional TF. Now you might also think, well, that's a bit weird because we're gonna basically have a joint state broadcaster controller that's gonna publish the joints for those two wheels here. And then the robot state publisher is gonna listen to those joint states and publish the TF. And here we are publishing another TF. And yes, that's not a problem. You don't necessarily need to publish all the TFs from the same node, from the same place, okay? You can have the TF for the joints of the robot published through the robot state publisher, but you can also publish from anywhere, from this controller, you can publish an additional TF. That's not gonna be a problem. So here we publish the odom2 base. So what is gonna be the TF? The first one is gonna be named odom, that's a new frame. And odom to what? Actually, here it's not odom to base link, it's odom to base footprint. Okay, because we have defined the base footprint link for the robot. If I go back to the parameters, you see the default one is odom. Okay, so we're gonna keep the same, I'm still gonna provide it. And then base link. Okay, so if I keep this, that's not gonna be correct. I need to change to base footprint. So I'm gonna go back here and say odom. So odom is a string base footprint. Okay, this one is very important. And even if this one by default is odom, sometimes it's also better to just still provide the parameters. So in case later you can change that if you want. Okay, so that's for the odom TF. We have some parameters. We have pose covariance diagonal that I'm gonna put here. Okay, so I can put a space to make it better. And then we have twist covariance diagonal. And I'm not gonna go into much more details about that. You see the default values are 0, but if I go here, you see these values should be tuned to your robot's sample odometry data, but these values are a good start. And well, basically any configuration I've seen is using those values. So I'm just gonna take those and put them here. And I think it's the same. It's the same for both. Yes. Okay, so now when you see this in another configuration, you know that it's just the default values that you can use from the documentation, the one that they recommend. I'm not an expert in covariance, so I'm just gonna leave it like this. Okay, if you are more expert than me, then feel free to modify those parameters, but those should work fine. All right, so we go back here and then, well, we have open loop. We're not gonna use it because we want to close loop control and by default it's false. I'm gonna use this one still, enable odom TF. It's true by default. And I'm gonna put it here, enable odom TF. I'm still gonna put true. Okay, so just in case later we want to start the controller but not publish the odom TF, we can do that. Then, well, this we're gonna leave it like this. Okay, so you have the description for each parameter. You might decide to use some of them if you want. I'm also gonna put the publish rate. You see that's the publishing rate in Hertz of the odometry and TF messages. And you see this is a double. By default is 50 Hertz. So I'm gonna put it here, maybe here, publish rate. It's okay, publish rate. And well, let's skip 50. Here it should not be, so you see the rate here is an integer, the rate here should be a double. Make sure you get that correct, otherwise you're gonna get some errors. And that's an important thing here is if you have a 50 rates here, 50 hertz, but if you only have 10, then basically this is gonna make all the controllers run at 10 hertz. So if the controllers run at 10 hertz, you cannot have a 50 hertz ODOM TF. Okay, so that's also an important thing to note is if you have to precise some kind of frequencies and publish rates inside controllers, then if this is lower than the global update rate, you might have some issues, or simply you might be surprised at why it's not working at 50 hertz. Why you don't have new data at 50 hertz? Because this one says that controllers are gonna run at 10 hertz. Okay, so I'm gonna put 50, 50 and 50. Okay, you can put higher. If I put 100, it means that the controllers are gonna run at 100 hertz, including that one. But then the publish rate for the ODOM is still gonna be 50. Okay, so it's not gonna publish the ODOM at 100 hertz, but only 50. Okay, so that's a nice way to cap this, because maybe you will have 1000 hertz. You don't need an ODOM at 1000 hertz. Okay, so that's just for the explanation. I'm gonna put back 50 here. And to finish, well, I'm gonna use velocity limits. This also is optional, but I'm just gonna show you how to use it. It can be a nice thing to have, okay, because you might not want your robot to have a too high velocity or acceleration, deceleration, etc. Okay, so how to use this? Well, actually, I'm using, well, you see, this is an important thing, is I was using a different branch. I'm going to use the master branch, which corresponds to the latest ROS2 distribution. And, well, it doesn't change for the rest because the other parameters are going to be the same. But one thing you can see already is for this velocity limit, here we have linear X, max velocity, mean velocity, etc. If I go to humble, which is an older ROS2 distribution, then we have linear X, and you see we have has velocity limit. So we have a Boolean already to enable velocity limits or not. And then we can set the max velocity. But with the new here, with the current one I'm using for recording, we don't have the has velocity limit. So I guess by default it's enabled, and we just need to provide a value to set a velocity limit. Okay, so make sure that depending on the ROS2 distribution you use, make sure you use also the correct, you see on the left, the correct branch for your distribution, because the parameters might be a bit different. So let's specify a velocity limit. How do we do this? Well, it's quite simple. You do linear and then dot x dot velocity. Actually, it's max velocity. Let's go back here. Yes, max velocity. We also have mean velocity, and it's a double number. So max velocity, and let's say 1.0, and then linear dot x dot mean velocity is going to be, let's say, -1. And then you can tune those values. You can increase them. This is quite low. Okay, this can be nice to start with a low value just in case. Because if the controller is working in a weird way, at least you're not going to run the robot at 100 meters per second. And we go down here, see we have X, and we also have angular Z. Okay, because for diff drive, we can basically say move forward or backward, and we can say turn right or left. So angular dot Z dot max velocity 1.0 angular Z mean velocity -1. Also pay attention not to make typos, because if you make typos in the parameters, you might not have an error. It might just be ignored. All right, and I think that should be it. So you see, with this controller, it was a bit more work to find the different parameters and to set them as we need. Some of them are really, really important. For example, those ones here, they're really super, super important. Then the good thing is, once you know how to set the diff drive controller for one robot, then for another robot, it's going to be pretty much the same thing. You just replace the values. And in many examples in ROS2 control demos and other examples that you find online, you're going to find similar configurations, okay? And what people usually do, and what I did myself also when I learned ROS2 control first, is Well, you just find a configuration and you copy paste for your project, and then you tweak some values and you hope that it works. The good thing now, I hope, with this lesson is that now you understand actually where those values come from, and you understand a bit more about how to set them up, how to tune them, and how to use the parameters that you actually really need. Okay, so make sure you save the file. All right, and the controller configuration is now complete. Now that you have a URDF, a ROS2 control tag in the URDF to specify the hardware interface, which now is a mock component, and now that you also have a package with a config for the different controllers you want to use, we can actually start everything. And I'm first going to do that directly from the command line. We're going to start each node one by one so you can understand what we need to start. And in the next video, we're going to actually create a launch file. Okay, so usually I recommend to do this if you can, is to start the stuff directly, understand what you need to start, and then add it into a launch file. Okay, so the first thing we need is the robot state publisher. This should not be new to you. So ROS2 run robot state publisher. This is really the central piece of any ROS application. Okay, robot state publisher. So we start the node and then ROS args with a parameter -p. The parameter name is robot description. And then, well, here we have this syntax to use Zacro. So $ parentheses, Zacro, close the parentheses, and then space. And we need to specify the Zacro file. So that's going to be this one, myroboturdf.zacro. So what is the path? Well, I'm just going to use this terminal. We're going to go to our workspace, my robot description, URDF. Okay, that's going to be here. I do pwd. I just copy this path. So make sure you copy your path because you don't have the same username as me. And then slash myroboturdf.zacro. Okay, you can just copy to make sure you don't make any typo. Okay, let's just clear this. All right, so ROS2 run robot state publisher with ROS args -p. The parameter name is robot description. And then we use the Zacro command with the file. And this file contains what? Contains all the links, all the joins, and the ROS2 control tag. I press enter, you see robot initialized, or you see other logs, and that's the first thing we have. Okay, we have our robot state publisher node. Now, what we're gonna do is we're gonna start the controller manager. Because if you remember from the introduction, we're gonna start some controllers, and those controllers are gonna be bound to some hardware interfaces. But how do we do this? We need a controller manager that's from the ROS2 control packages. So we're gonna do ROS2 run controller manager. So actually we have a package named controller manager, and inside we have a ROS2 control node. Okay, you should use the auto completion. If it doesn't work, then make sure that you have correctly installed the ROS2 control node from the introduction. And we are not just gonna start it like this. We're gonna give it the parameter file here that we have created. And so it's gonna have all those parameters and all the controller configurations. So we do ROS args, and then not just one parameter, but params-file. And we're gonna specify, so here just home / I use the absolute path. Okay, it makes things easier. So that's my username, and then ROS2 workspace source my robot bring up config, and it should be only one. So my robot controllers.yaml. All right. So ROS2 run controller manager, name of the package, the name of the node. Actually, the name of the executable is ROS2 control node, and we pass the parameter file. Let's see if that works. So what do we have here? So you see subscribing to robot description topic for the robot description. So that's why you need to first start the robot state publisher, and then we're gonna get the URDF as well. Update rate is 50 Hertz. Okay. We have some warning here, but it's not a problem. And then you see loading hardware, mobile-based hardware interface. And you see here mock components, generic system. This is what we have specified in the ROS2 control tag. Okay, that's this name here that you see, and that this plugin that you see. Okay, And then we have all the stuff with configure, activate. That we're gonna come back to this later when we create our own hardware interface. Okay, so now what do we have with this? Well, we have the controller manager. If I do ROS2 node list, you see we have robot state publisher and we have a controller manager node. Okay, you see the name is controller manager. That's why also in the YAML file, we have controller manager here because that's the name of the node. I know it's a bit confusing. So the controller manager is the name of the package. And then we have ROS2 control node for the executable name, but then the node name is controller manager. That's just how it is. All right, so now what's missing is actually we need to kind of activate the different controllers. We need to start the controllers because we have the name of the controllers here. With the configuration, the controller manager knows about them, but we need to start them. How to do this? I'm going to do clear here. So we have two terminals already occupied, robot state publisher and controller manager. Here we're going to do ROS2 run controller manager. So same package, but then we have a executable named spawner. Okay, that's going to spawn, that's going to start a controller. I'm going to put that here so we see the logs. And what's going to be the name? The name is the name that you have defined here. So I can copy this name here, join state broadcaster, and put it there. And press enter. And you see, so this node, this spawner node, is just going to start spawn something and then exits. Okay, and you can see, so loaded join state broadcaster, it's configured and activated. And here on the controller manager side, you see that we are loading the controller, okay, with some logs to say all available state interface will be published, etc. All right, still from the same terminal, I can do ROS2 run controller manager spawner, and this time diff drive controller. Make sure it's the same name, okay, as the one you have defined here. And I just press enter. Let's see what we have. Okay, it's working. And you see we have logs here, loading controller. You see it's gonna use the arguments from the parameter file that we have specified. Okay, and now the robot is actually running with ROS2 control. It's a fake hardware, okay, it's a mock component, but it's working correctly. How can we verify this? How can we actually see something that works? Well, I'm gonna run RVs. ROS2 run, RVs2, RVs2, and I'm gonna give so with -d, I'm gonna give a configuration. And actually in the package that I gave you in the my robot description, we have a RVs config. I'm gonna use that one. Okay. So I put the absolute path, ROS2 source, my robot description, RVs, and URDF config.rvs. All right. And you can see the robot here. So nothing special, but one first thing you can notice is we don't have an error for the wheels for the TF. It might seem normal, but actually it's a good sign. It means that the join state broadcaster is working correctly. Okay, because now we don't have a fake join state publisher anymore. It's the controller from ROS2 control. And you can see that we have the correct TF for the wheel. They are not moving, of course, but they are correctly published. In the fixed frame, I can also, you see, I can choose ODOM. All right, we have a new TF ODOM to base footprint, which now you see, well, it's the same. You can just check the TF. It's at the same place because the robot hasn't moved. Great. If I do, so I have RVs here, and I'm going to control the robot from that terminal here. So if I do ROS2 node list, as you can see, I have my controller manager, I have my robot state publisher, and then I have one node for each controller, okay, plus one node for RVs. If I do ROS2 topic list, I have quite a lot of stuff, but you see I have my diff drive controller /cmd-vel. Okay, so you probably are familiar already with a cmd-vel kind of topic where you send a twist message with a linear and angular velocity. And this is, you see, this is what's used by the diff drive controller. So for the topic name, I'm not sure, but you might be able to change it from the parameters. Anyway, we're going to use that one. So I do ROS2 topic info with this. Okay. One thing you can notice is usually for this kind of topic, we use a twist, but here is a twist stamped. So if I do ROS2 interface show with twist stamped, we have still our twist with linear X and angular Z. That's what we need. But we also have a header with, you see, a timestamp. And that's quite important. That's going to be used to decide if the command is recent enough or not to be taken into account. All right, so just know that when you publish on this command velocity topic, you need to specify a twist stamped with the current time. Now there is a node we can use directly from the terminal, ROS2 run teleop twist keyboard and teleop twist keyboard. So this way we can send the command velocity directly by moving arrows on the keyboard. That's going to be much easier to visualize. And actually we cannot just run it like this because it's going to publish a twist message on the /cmd topic. So we need to change first ROS, so ROS args with -r to rename the cmd vel to, and actually what was the, so ROS2 topic list, it's that one. Okay. So we make sure that instead of publishing on cmd-vel, we publish on that. Anyway, if you see it doesn't work, you start rqt graph and you can easily see that topics are not the same. So we change the name of the topic, and then there is an option for this teleop twist keyboard that's quite easy. We do another, so we do -p for parameter and stamped with colon equal true. This is going to add a header with a timestamp. Okay, so we don't need to do anything else. All right, I press enter, and then, so I'm gonna have this on one side. I'm gonna put Arvis here, and I'm gonna zoom out a bit. I choose Odom as the fixed frame, and then you see you have the commands to make the robot move. Let's try, and you see that it is working. Great, our robot, even if the hardware is a fake hardware, but we have correctly configured the controllers and kind of the stack with ROS2 controls and the different nodes we need to start so that we can use ROS2 control with our robot. All right, you can see it's working. We see the wheels are turning, and we even have this TF, this new TF, Odom to base footprint. In this video, we are going to write the launch file so that we can start everything that we have started in the last video. So the robot state publisher, the controller manager, we're gonna spawn the different controllers. We're also gonna start Arvis so we can have this view, okay? So I'm gonna stop everything, just make sure you stop everything in case. All right. And close everything. We're gonna come back to our package, my robot bring up. Here we have a config folder. We're gonna add another folder named launch. So inside my robot bring up at the root of the package, you have launch and config. In the cmake_list.txt, very important, you go here and you have config, you're gonna put launch. Okay, the order doesn't matter. You make sure you install the config folder and the launch folder. That's all we need to do here. So I'm going to close this and we don't need to come back to the cmake_list.txt anymore. Now in my launch folder, I'm going to add a new file, which is going to be, well, let's say my robot.launch. And as you know, as I love Python launch files so much, I'm actually going to do the XML one. It's going to be much easier. I'm still going to show you the Python one afterwards, okay, but I'm going to write it in XML. I really recommend XML anyway. I think the Python launch file is overly complicated for pretty much nothing. And just in case you really need to use Python for a launch file for some functionalities, you can always include that part inside an XML launch file. Okay, so let's start launch, and we have a launch tag, that's it. And what is the first thing we need to do? Well, we need to start the robot state publisher. And with this, we also need to pass the URDF. Now, the good thing is, I'm not gonna reinvent the wheel here. If I go to my robot description in my launch display.launch.xml, that's what we have done actually. We have already started the robot state publisher with the URDF. And you see the syntax is a bit particular. So instead of just reinventing the wheel and making mistake, I'm gonna take that one. So I'm gonna take the variable here, URDF path. I'm gonna copy that and I'm gonna put it here. So make sure everything is still correct. Okay, we're gonna use the my robot description package, that's this one, and we're gonna get this file. And then we're gonna start the robot state publisher, which is this node here. All right, robot state publisher, param name is robot description with the command zacro and the path. Great. Then we have the RV stuff. I'm gonna keep that for just at the end of the video. We don't need the join state publisher GUI. This was just for testing. Okay, we're gonna use the join state publisher from the ROS2 controllers. So what do we have next? After the robot state publisher, we need to start another node. We need to start the controller manager. So if you remember what we did on the command line is from the package controller manager, and the executable is ROS2 control node. I'm gonna close it like this so that I can add a parameter. So param, and we're gonna use from because we're gonna include the config file here, the myrobotcontrollers.yaml. And well, you could use a variable if you want. I'm just gonna put it like this. So find pkg share. We use find pkg share because everything is installed inside a share folder. I need to put the name of the package. So my robot bring up is this package, and then slash after the parentheses is going to be config slash my robot controllers.yaml, and I close the param tag. All right, so we start the controller manager node with the parameters here. And so the controller manager is also going to listen to the robot description topic from the robot state publisher. It's going to get all the information with the ROS2 control tag here. It's going to get the information with those parameters. Okay, that's everything we have specified. So now what we can do is we can spawn our different controllers. So we're going to use node because we did the ROS2 run. Okay, so there's going to be a node here. Controller manager exec is spawner like this. And then we were providing some arguments. So we're going to put args and just the name of the controller. So joint state broadcaster. If you're not sure, you just take the name you have created here. We spawn that one, and then node pkg controller manager exec spawner again, and we spawn the diff drive controller. Okay, so we spawn the two controllers that we have in our application. And that's it. Now we have also started RVs because it's nice to visualize what's going on. Okay, to validate that it's working, RVs is often the best way. So we're gonna start RVs, and actually I don't need to write the code myself because I've already written it in the display launch XML. Okay, so I'm gonna take my RVs config path variable and put it there, here in the launch file. Okay, make sure it's the same config that we are using from my robot description package. And then I can take my RVs node right here. So I do RVs2, and then the arguments -d with the configuration. I'm gonna save, and the launch file is now complete. All right, so we start, you see, one node here, the robot state publisher, and then we start the controller manager. Then we spawn the two controllers, and we also start RVs. Now for the teleop keyboard, well, the teleop keyboard is something we're gonna start on the side. Now, what I'm gonna do as well is, because you see we are using, so from this package here, we are using the robot state publisher package, the controller manager package, and we also need the my robot description package, plus ROS2. So I'm gonna add those in the package.xml. I'm gonna add here after build to depend, I'm gonna add exec depend robot state publisher, exec depend, and then exec depend with controller manager, exec depend, and then another exec depend with my robot description. Okay, I close the tag. And finally, exec depend ROS2, and I close. All right. So that's going to make things a bit cleaner when we build the workspace. Let's save that. All right. And if one of those packages doesn't exist here or is not installed, then we're going to get an error when we build, not when we run the launch file. So let's go ahead. Let's open a terminal. Let's go to our workspace and call const build. Okay, I'm going to source. And I'm going to do ROS2 launch. Launch my robot, bring up with, so it was my robot dot launch dot XML or Python should be the same. Okay, you see this time we have all the logs in the same terminal. All right, as long as you see this blue and this green, it should be okay. You see that we have processed has finished cleanly. This is the spawner. Okay, so when we spawn a node, if you remember, it's just gonna spawn the controller, and then the node, the spawner node itself is gonna finish. So this is not a problem. This is normal. And RVs is here. All right, and I'm gonna open a new terminal here and just say ROS2 run. So we have the same thing. We have ROS2 topic list is gonna be the same. We have the div drive controller cmdvel. Okay. And so if I go back to my commands, I can find this one, the ROS2 run teleop twist keyboard. I changed the name of the cmdvel topic, and I also add a stamped parameter. Okay, let's see if that works. Should be working. It works. So actually, you see the robot wheels are moving, and I'm my fixed frame is the base footprint. If I change to Autumn, then you can see the robot moving from its origin point. All right, and I will just do one last thing. I do arc graph. All right, I'm gonna hide those. And so what do we have? We have, you see, centerpiece is the robot state publisher publishing on the TF topic. And also on the robot description is publishing the URDF. You have the controller manager here. And then we have the joint state broadcaster publishing on the joint states. So this one is going to receive the data from the hardware, which for now is a mock component. So it's a fake hardware. And it's going to publish to joint states, which is going to be received by the robot state publisher and then publish the TF. Now we have the second controller, which is the diff drive controller. Okay, and you see that, well, our application in this case, if you remember the introduction, I had a box on the left, which was the application. The application is the teleop twist keyboard. It's going to send the cmdvel command, okay, which is going to go to the controller. The controller is going to control the wheels, and also publishing on TF is going to publish the ODOM TF. All right, so you see we have two nodes publishing on TF. Okay, and that's pretty much it for now. All right, that's also the end of this ROS2 control crash course on YouTube. I hope you could learn a lot and get a better understanding of how ROS2 control works. So you have seen how to adapt a robot with ROS2 control with the URDF tags, the configuration for different controllers, and the launch file to start everything. Now, if you use ROS2 control, it's probably so that you can control real hardware. And here comes the next step for you. you will need to learn how to create a hardware driver and a hardware interface so that you can bridge the ROS2 controllers with your custom hardware. And this is exactly what I teach in my full ROS2 control course, which contains 7 hours of video content, more practice, and downloadable code templates for your own projects. If you like the way I teach, you will love this course. Here's actually an overview of what's inside the course. So the course contains 7 sections, okay? We have the introduction section and then the section 2 on how to adapt a robot to ROS2 control with a mock component, with mock hardware. So that's basically what we have done here in this crash course, more or less. There's one more lesson here, but that's basically what you did. And now the most important part is actually this one, how to create a hardware driver and how to write a hardware interface for ROS2 control. So I will show you how to create a pure C++ hardware driver, okay, give you some tips on how to do that and also how to include this driver inside the ROS node. Then we will write a hardware interface for ROS2 control, okay? We'll create a package, we will correctly configure the package, build it, and I will explain everything you need to know so that you can create your own interface for your own project. We will then we will do a project. So the section 5 is a complete new project. Okay, so for now we only have a mobile base, but in section 5, we are going to add a robotic arm on top of the mobile base and control it with our own hardware as well. Okay, so you see I have some motors here. And so we're gonna do the whole process again to adapt the robot to ROS2 control, to add also a hardware interface and to use the hardware driver for those motors. And then we have a complete setup. Also an extra step on how to use ROS2 control with the Gazebo simulator. And that's not all, there is also another section, 1 hour, on how to create a custom controller. So then after this, you can create your own custom hardware interface, your own custom controller. Okay, you know how to start everything and you will have full control over ROS2 control. All right, thank you for watching and I hope to see you in the course.